Imagine you have a mathematical map of the geometry of a perfectly cubic piece of cake. Each side of the cake is length h. Our value of h is a finite value, such that our cake has a finite volume of v equals h to the third power. Now, let's take that cake and look at it from a bird's eye view. Suppose we cut the cake in half. Then we pick one piece of the cake and we cut it in half again, and again, and again, until we have cut the cake in half an infinite number of times. Each piece of the cake gets smaller in width, but keeps the same length and height. Now, let's take these slices of cake and stack them into a staircase, such that one side of the slices all form a single wall. Rotate our perspective a bit, and here we find something very interesting. I remind you that we're looking at the height of this cake staircase right now. How much frosting would it take to cover this side of the cake? Since the sum of the heights of these slices of cake is the height of the staircase, and each step in the staircase is a slice that has the same height h, then we should be able to calculate the total height of the staircase by multiplying the height of each step by the number of steps. We plug in our values and... oh wait, we cut the cake an infinite number of times. This means our total height is h times infinity, or our total height is infinity. Without breaking any mathematical rules, we took an object of finite volume and gave it infinite surface area. But this cannot work in reality, which raises a profound question. Is mathematics truly the language of the universe? Okay, clearly we cannot create infinite surface area out of finite volume in the real world. So why doesn't this cake thought experiment hold? Mathematically, where does it break down? If the width of each slice is getting cut such that it's half the size of the previous slice, then the width can be described as follows. Whereas n is the number of slices and the width of the nth slice is w subscript n. We can then consider what the behavior of the width is by finding its limit. Clearly, we can see that as the number of slices approaches infinity, the width of the nth slice approaches 0. But on the other hand, if the number of slices n approaches infinity, then the number of edges approaches infinity. We therefore can calculate the surface area of the number of slices n to be, whereas n is the number of slices, a is the area of an edge of the cube, and s of n is the surface area of n slices. Thus, therefore, going through the process of slicing the object of finite volume h to the third power and rearranging the slices has yielded us a staircase with infinite surface area. The reason why we can't do this in reality is because the universe has rules that our 3D plane does not abide by. We cannot divide objects infinitely, because objects do not have infinite precision. Specifically, objects in the universe cannot be divided infinitely because objects are composed of atoms that have approximate sizes, which are composed of particles, protons, neutrons, and electrons. Protons and neutrons are composed of subatomic particles, and then there are electrons that are already subatomic. Once we hit the subatomic level, there is nothing smaller that we know of. You're kind of stuck at the Planck length. Additionally, our knife is not infinitely thin. It has a shape that can only fit so many times along the width of our cake. The lack of adherence of our mathematical representation of the cake to these two principles are where the disconnect between our mathematical representation and reality lies. But this doesn't necessarily mean that mathematics isn't the language of reality. All we have to do is use more sophisticated math to simulate cutting the cake to represent the scenario. If it doesn't make much sense to go smaller than the Planck length, which has a finite value, then n cannot approach infinity. It has to have a maximum value. Thus, we can revise our scenario as follows. We require that the limit, as n approaches a maximum value of n max, of the width of the slice is greater than or equal to the Planck length, whereas n is the number of slices, w sub n is the width of the nth slice, and L sub p is the Planck length. And since we already know the formula for the nth slice, we have that. Therefore, n max is equal to the log base 2 of the ratio of the height to the Planck length. Since h and the Planck length are finite and non-zero, n max is finite. We could continue with the sophistication to try to include the width of the knife, and by accounting for the amount of cake that is lost in various ways, like by getting stuck to the knife. But you get the idea. We can represent reality more accurately by incorporating more information and raising the level of sophistication of our model. But while upping the sophistication in specific ways can resolve the disconnect between math and reality in specific situations, another question arises. Is our system of mathematics as a whole sophisticated enough to represent reality as a whole? That is to say, is math the language of reality? Can it be used to explain all of reality? How can we be sure when our mathematical physics are all based on approximations at the fringes of their respective theories, and when on the most fundamental level, the quantum level, our best mathematical interpretations are non-deterministic? In all experiments, there are errors, which skew our data from matching our mathematical equations that describe their behavior. These errors cause uncertainty. Uncertainty can be introduced in a number of ways. Systematic errors, errors caused by a mistake in the way that the experimental procedure is carried out, instrumental errors, an error introduced by the maximum level of accuracy of your instruments, human errors, an error introduced by human mistakes, and random errors, which are the result of unpredictable or unknowable changes. There will be some errors, but of all four of these broader archetypes of variables, one of them cannot be solved. On a quantum level, we have found an uncertainty that seemingly cannot be circumvented. The Heisenberg uncertainty principle, whereas sigma sub x is the uncertainty in position, sigma sub p is the uncertainty in momentum, and h bar is the Planck constant, not the Planck length. In the simplest case, where mass is constant, this means that since momentum equals mass times velocity, and the mass is constant, the uncertainty in momentum is equal to mass times the uncertainty in velocity. Plugging that back into our uncertainty, we find, meaning at the absolute best, the uncertainty in position is equal to h bar over 2m times the uncertainty in velocity. And the uncertainty in the velocity is equal to h bar over 2m times the uncertainty in the position. This is not a mere uncertainty of our experimental instruments or human biases. This is a random error. But as far as we can tell, it is not as simple as being an unpredicted variable. It is a fundamental limit of information in quantum systems. This is a graph of a quadratic equation, and this is a graph of a quartic equation. As you can see, when our equation is a higher order polynomial, we are able to capture more sophisticated data trends. But this is not always to our benefit. Suppose a projectile is launched vertically, and we generate our position time graph using this data. Here, our y variable is the height and our x variable is time. We know that our current physical understanding implies that this trajectory is a parabola, and indeed we have a solid determination coefficient, r squared, of 0.9969, where the closer you are to 1, the better. However, when we plot the equation that we get from using the quartic regression on this data, we find that we get an even better determination coefficient of r squared equals 0.9999. Yet, we know from our Newtonian mechanics that the equation should take the form which is a quadratic polynomial. But how can this be? A quartic model captures more sophisticated behavior than a quadratic model. Isn't more sophistication preferable? After all, our statistics say that our quartic equation is a better fit for the data. What's happened here is that we've used a model that is more sophisticated than the reality of our scenario. This is the problem of overfitting, where our model fits too closely to our data as a consequence of the natural errors in our experiment. If we refine the accuracy of our experimental procedure and instruments, then we should in principle find that a quadratic equation does actually fit the data better. But what about experiments in fields like quantum mechanics, where we have inescapable errors that cannot be circumvented by refining our experiment? Perhaps we could use a form of equation that can accurately connect any set of data points. Enter wave equations. Our standard physical models, like the quadratic equation for projectile motion, don't always perfectly describe reality. Even with the best instruments, our experiments will still contain errors. And as we've seen, more complex models like quartic equations might fit our data better, but not necessarily in a meaningful way. This is where mathematics and statistics step in, allowing us to compare models, refine our approaches, and understand the limits of our information. Yet, this process isn't without its own pitfalls, like overfitting, where a model can become too sophisticated and start capturing noise rather than the true underlying patterns. Still, the beauty of mathematics lies in its adaptability. So, while our current mathematical representations may not be perfect descriptions of reality, they are the closest tools we have for making sense of it. If there is such a thing as a language of reality, then surely it must be mathematics. Because even when math falls short, it is math that we use to replace it. Thanks for watching.